Okay, so what we're going to be looking at actually for the next few weeks is what happens when we say, hey, let's make acceleration the same for at least like some amount of time. And constant acceleration is kind of interesting because when we think about objects that move around, a lot of times we think about people, or we think about machines that are operated by people. And those have this inherent unpredictability to them. And so we can make predictions using biology, right? Like we could predict that like if there's a thirsty cat, we can kind of make a prediction that it's going to go toward water, but there's no mathematical equation that we can use to determine where an animal is going to be at a certain time or how long it's going to take to get somewhere because its motion changes. And so we tend to think about like, well, we really can't make a lot of predictions, but it turns out that much of the time, motion is predictable. Much of the time, motion is not driven by biological organisms, humans or otherwise. And even when things are driven by biological organisms, a lot of time, for at least brief periods, it's highly predictable. And that's because a lot of times, objects are experiencing at least a relatively constant acceleration for some amount of time. So what we're gonna start working on are some new skills. One of those is to make predictions about our motion graphs. If we know that an object is accelerating constantly, and we know the direction of acceleration, or maybe there's none at all, we can then predict how velocity will change. And if we know what the initial velocity was, at least what direction it is, we can predict that better. And we know how the position is going to change as well. And again, if we have a little bit of information about the position, like whether it starts at 0 or 1 or -1 or in a negative part of the one-dimensional line, we can make pretty reasonable predictions about how an object is going to move. And then, so that's drawing graphs. Like if I tell you an object has constant positive acceleration, it starts with a negative velocity, like what do the graphs look like? You can actually figure that out. And then the next skill is if you look at motion graphs that are showing constant acceleration, can you look at those graphs and be like, I can tell you how this object is going to be moving. Based on these graphs, I can tell you the object is going to move this direction for a while, slow down, reverse direction, and start speeding up the other way. Okay. And then watching an object and using that to determine what its acceleration, velocity, and position graphs would look like versus time. Okay. And it all starts with the idea that we know how these graphs are connected to each other mathematically. So if we start with the assumption of constant acceleration, which isn't unreasonable, it's really easy to get constant acceleration, then we know that acceleration is the slope on a velocity versus time graph. Mathematically, that's going to be true. Acceleration is the rate of change of velocity. Velocity versus time graph, the rise over run is the rate of change of velocity. So at any time, the acceleration of an object will be equal to the slope of the velocity versus time graph. If we have a constant acceleration, then we're going to have a constant slope. That means that the velocity is going to change by the same amount for a given time period. It's going to be a straight line. If there's no acceleration at all, then we might end up with a perfectly horizontal line. If there is acceleration, it's going to be a diagonal line. Okay? If there's constant acceleration, then an object is likely to be moving, at least at some point, and its velocity is going to be changing, and we should be able to predict how its position changes, because if we have constant acceleration, that's going to result in a constant slope on a velocity versus time graph. And we know that a velocity versus time graph tells us the slope of the corresponding position versus time graph, which means, as you saw in the Match This Motion lab, if we have a velocity versus time graph that's a diagonal line, we should get a position versus time graph that's a curve. We'll look at the equations in more detail next week, but it's gonna be a parabola. Okay, if we have constant acceleration, non-zero acceleration, then our velocity versus time graph will be linear, and our position versus time graph will be a parabola. That means if we have constant acceleration, we have a relatively limited set of graphs that we're likely to see. We're gonna see straight lines on a velocity graph, probably parabolas on a position graph that might be upwards facing, they might be downwards facing. Our velocities might be up and to the right or down and to the right, or maybe perfectly horizontal. There's a whole bunch of possibilities, but it's relatively limited. So what I want you all to do today is to play around with making some of those predictions. So I'm gonna give you an example, I'm gonna show you how to make the prediction, how to test it, and then this is what I want you all to do for the rest of the period, okay? So the first thing you're gonna do is, in general, these are things that I could give you, but I don't think I need to. I think you could give yourself these same challenges. So if we were to think about an acceleration versus time graph, we're talking about constant acceleration now. So let's just pick an acceleration. Let's say that we have a constant negative acceleration. Do we know exactly what it is? We don't really need to. If it's constant, it's always the same. If it's negative, it's below the x-axis. So we're gonna have an acceleration versus time graph that's a horizontal line below, like y equals negative something or other, okay? And then we know that the acceleration is the slope of a velocity versus time graph. It has to be. The rate of change of velocity is gonna be the rise over run on a velocity versus time graph. That's the definition of acceleration, rate of change of velocity. So if I know that my slope on my velocity versus time graph is negative, then I know that my velocity graph is gonna be down and to the right. But the problem is, these are all down and to the right, and I don't know which of these it is, and they might look different when we evaluate the motion. So let's say that we start with an initial velocity that's positive. Again, we don't have to know what it is. Let's just say it's positive. So that means our initial velocity is here. Our constant slope on our velocity graph is gonna be negative, which means down and to the right, which means it's gonna look like this. Is it gonna get to zero or cross? Well, we don't really know, but let's just say, for the sake of argument, that we could probably engineer a situation in which we have the right combination of accelerations and initial velocities that over 5 seconds, this thing's velocity will look like this. That seems at least possible. We don't know what the magnitudes are, but I mean, you guys were walking around, so when you were using the motion graph lab, you know what it looks like when something is moving like 1 to 2 meters per second over the course of 5 seconds. We could pull that off, okay? And then we know that the velocity graph is the slope of a position versus time graph. Position versus time will show us, the slope on that graph will show us rise over run. Rise is change in position, run is change in time. The slope of a position versus time graph is velocity. And so if we identify the velocity at each time, that will tell us the slope of the corresponding position versus time graph. So let's do the same thing. Let's say that our initial position is negative. So let's just start here and see where we get. So initially, our slope is positive. So my slope is going to be up and to the right. But my positive slope is getting smaller and smaller in magnitude, closer and closer to zero. And by the time it hits 3 seconds, my slope is 0. So that's going to look something like this on here, right? Like a 0 slope looks like this. My position curve is going to start positive, and according to this prediction, roughly by 3 seconds, it's going to be horizontal. And then it's going to start becoming negative, and it's going to become more and more and more negative. So there's my prediction. the absolute numbers don't matter at all. Because we don't know what they are. We don't even know what object we're talking about here, although you will shortly. But the shapes are very reasonable, right? This is going to be our acceleration versus time graph. Our velocity certainly is going to be down and to the right. Our position certainly is going to have a positive slope initially that will become more and more and more shallow. If the object moves for enough time, eventually it's going to level off and then start becoming negative and steeper and steeper and steeper. And ideally, you'd be able to visualize this motion. But let's instead of trying to figure it out by looking at the graphs, let's see if we can engineer this situation with the motion cart. So I am going to, what we found today is that it looks like Bluetooth is enabled on your Chromebooks. So that's good. You might need to turn it on. So if the Bluetooth button isn't on your Chromebook, you should turn it on. And then when you turn on the cart, you'll get a little red blinky light. And if you click sensor data collection, it should find the cart. So this one says 143, and this one is number 143. So that's the one I'm going to connect to. And I want 3 graphs. I want to look at my acceleration and my position and my velocity. And what I said was I want a constant negative acceleration. I want an initial positive velocity and an initial negative position. So let's see how I can do that. The cart actually has an arrow on it. There's an arrow with a plus. This is the positive direction for the cart. So if I want the cart to have an initial positive velocity, I'm going to roll it in the direction of this arrow, so I can do that. I also have the ability to change the position of the cart. You probably can't see this, but on your computer you will be able to. This says position equals about 0.02, and I can actually zero that. So now it thinks this cart is at position 0, and it's this little middle wheel that measures the position. So if I want an initial negative position, I can just roll this and give it an initial negative. I'm going to make it about negative 0.5 meters. And the reason I'm going to make it negative 0.5 meters is because I know that these tracks are like 1.5 meters long. So if I started at negative 0.5 and I roll it, it seems like that's going to, it seems like a nice starting distance. I might be able to get it up to 0 or even past 0. So that might be kind of an interesting thing to do. Then the last thing I need to do is I need constant negative acceleration. And it turns out that if you have an object on a ramp, it will experience constant acceleration in the direction of the ramp. So if I take my cart and I arrange it so that its positive direction is up the ramp, then it will be experiencing constant negative acceleration. It's always going to be accelerating down the ramp. So let's see how that plays out when we collect data. Okay, let's see what we got. So obviously there's some garbage at the beginning and the end, right? Like I had to give it a little push here, and it bonked into the end here. But if we just look at the time period during which I wasn't pushing it and it wasn't hitting something else, it did have a constant negative acceleration. We can even see what that was. It looks like it was about negative 0.302, 0.25. It was like, I don't know, I guess kind of going up and down a little bit. And that's probably because actually the track is a little curved. So it's not a perfect ramp, but I mean, it's right around 0.3 meters per second squared in the negative direction. And then my velocity versus time graph during this time period, boy, that's a nice straight line that starts in the positive direction and goes into the negative direction, just like I predicted. And then my position versus time graph, I didn't quite get it to position 0, almost though. Like I was really close to position 0. That was just coincidental. But I can test my predictions, right? So what I would like you to do is if you think about this mathematically, you'll realize your acceleration can either be constant positive, constant negative, or zero. Your velocity could either start positive, start negative, or start at zero. And same with your position, which means there's 27 different cases that we could think about here. Now, many of those are sort of overlapping. We don't have to like look at the case where you have negative acceleration, positive velocity, and position zero versus position positive. Like, you could figure out what these things are gonna look like without having to go through all of them. But some of them are more interesting than others. What does it look like if you have an initial negative velocity with zero acceleration? What does it look like if you have an initial positive velocity with positive acceleration? How will the resulting position versus time graph look? So your goal is, one, to make predictions. I want you to predict what these things look like and sketch them out. So if you go to our module today, I actually made a whole bunch of these in the module, and you can just like download it and draw on it. I can't click on that, I keep forgetting. You can draw on that and there's like 6 or 8 of them, so you can play around with that to your heart's content. It starts with the prediction. You make the prediction first, and then you test it with the motion card, okay? All right, I'm gonna turn the video off.